Hello, my name is Alexandra Mitzi and the topic of this presentation is the Pushover-Analysis workflow for SOFiSTiK version 2014. It is possible to apply pushover method in previous program versions, but in the 2014 version many improvements have been made into the direction to make this implementation much easier for the user. This video covers the following topics regarding pushover analysis: the revision of the workflow for implementing pushover analysis into SOFiSTiK, the possibility of an axial force moment interaction diagram definition for the implicit hinges, and the improved visualization of results concerning pushover analysis. At this slide, we see a simplified explanation of the pushover analysis method according to the ATC40. Pushover analysis is a static nonlinear procedure where the magnitude of the structural loading is incrementally increased by a certain predefined pattern. Then the so-called pushover curve is obtained, which represents the force displacement diagram of our multi-degree of freedom system under the load pattern. Usually we choose the base shear force and the roof displacement as characteristic values for this diagram. Next step is to transfer the multi-degree of freedom system into an equivalent single degree of freedom system. After this, the capacity diagram can be obtained, which is plotted in spectral acceleration and spectral displacement values. By taking into account the hysteretic energy, we obtain an equivalent viscous damping, which will give us finally the reduction factors for the response spectral diagram. The blue line here represents this reduced response spectral diagram, and the red line the capacity diagram, and the intersection of them give us the performance point of the structure. The system that has been chosen for this presentation is a 2D steel moment resisting frame. 275 structural steel type is used as material, and two different wide double T-beams steel profiles are used as cross-sections. The 340 wide double T-beam for the columns and the 240 wide double T-beam for the beams. Here we see an overview of the SOFiSTiK workflow for pushover analysis. I will show the example in SOFiSTiK in accordance to those steps, so we will return during the presentation into this slide and explain better what this slide shows. The nonlinear properties of the system can be defined either by full material nonlinearities, for example with nonlinear beam, quad or brick elements, or by assuming that the nonlinearities will be concentrated in few discrete points, for example in the beam-column connections. The second approach is the most widely used and is being implemented by the definition of the plastic hinges into those discrete points. In our example, this approach has been chosen. Into the module AQUA, the material, cross-sections and the plastic hinge properties are defined. Major improvements have been made regarding the definition of the plastic hinges in the version 2014. One new possibility is the definition of an axial force moment interaction diagram. The input procedure of a PM diagram is the topic of another video for the 2014 features, so it will be not described here. So we can go now to the example made in the SSD environment. Two different workflows have been defined, one for the column and one for the beams of the system. If we go to the report browser, we can have a look at the hinge workflows that have been defined. So for spring material 111, which corresponds to the column of the system, we can view the axial force displacement workflow and also the moment rotation workflow. We can see here at the moment rotation diagram that an ideal elastoplastic workflow has been defined. In the next graph, we see the interaction PMY diagram. The same stands for the spring material 211, which corresponds to the beams of the system. Next step is to model the system and assign the hinges in the connection between the columns and the beams, and at the bottom of the columns, namely where we expect the plasticity to occur. I have already defined a simple steel frame system into SOFiPlus in order to show the steps for applying pushover analysis into SOFiSTiK. The procedure, of course, is the same for any kind of structure. So I will show now how easily you can assign the hinges into the beam elements into SOFiPlus. First I go to the Filter tab and select to show only the line elements. Then I go to the Structural Elements tab, and first I select the bottom columns of my structure, go to Modify my line, and I assign at the start a working load of 111, which is the Hinge workload for the columns. I choose Apply, and we can see here that I have applied my hinges. Next step is to apply the hinges into all the beams. So I check them all. I again go to the Modify the structural lines, and I apply the 211 spring workload for the start and also for the end of the beam. I check Apply, and again we can see here the hinges into the beams. I export my model and then we go to the SSD and the animator, and we can see here that we have the hinges at the beams, at the start and at the end, and also at the bottom of the columns. Third step is to define the pushover load pattern. Usually the load pattern that is being chosen corresponds to the fundamental eigenmode of the structure. I have already inserted the eigenvalues SSD task, and here at the first tab I can set some basic properties for the eigenvalue analysis, like the number of the eigenvalues. I leave the default settings for the damping, and I choose to convert the load case number 2 into masses in order to get the correct mass matrix of the system. So if we check at the animator, we can see here the first eigenform, the second one and the third. If we go to the report browser, we can see here at the table eigenfrequencies that the first eigenmode with the load case number 9001 gives around 80% of the mass of my system. So this is the basic eigenmode. We go back to the SSD, and next task is called pushover load case, and here I define my pushover load. At this stage we have to mention that depending on the type of the pushover analysis, force or displacement control, two possibilities for the definition of the pushover load exist. So if we go at the manual of SOFiLOAD, for the record AQUA, which comes from the word acceleration, if we go at the type record, we can see here that when we choose node, we get the pure nodal loads from mass multiplied by acceleration. If I choose the disp command, this corresponds to displacement control analysis for the pushover analysis. At this example I want a load control analysis, so I select the type node. Then I define the direction, and next at the vector length I define the negative value of the load case for the first eigenmode. This minus input of the load gives the recognition to the program that this is a pushover load. By this input, I have defined a load pattern that comes from the multiplication of the mass matrix with the corresponding displacements of the first eigenmode. So I run this SOFiLOAD module, and if we go now to WinGraph and go to the load 1001, increase a bit the letters size, we can recognize that this load corresponds to the first eigenmode by this form here. Fourth step is to perform the nonlinear static analysis. In this step, we will apply the pushover load incremental linear structure in order to take the capacity curve. For this step, as a module is being used. By SIST probe theory 3, third order theory is being selected for our analysis. By performing third order theory analysis combined with the PM interaction workloads for the hinges, p-delta effects are taken into account. We use the command ulti and we create several load cases where the pushover load is applied incrementally along with the load case number 2, where no factor is applied with the use of the command ulti off. So we run. So we go at the report browser and we can see that 39 load cases has been created, and at this diagram we can see for the node number 100, which is a node at the roof of our system, what's the reaction in terms of displacement when we incrementally increase the pushover load. At the last step, we determine the performance point. For this, we need to define first the demand diagram. So we go to the task demand, and we can see here that two response spectra have been defined, one according to the Eurocode and one according to the UBC. So if I open the report browser, I can see for the load case 101, the demand diagram according to the Eurocode for 5% damping, and for the load case number 102, we see the UBC diagram for 5% damping again. Performance point task is the final step of our pushover analysis, and where the new command push is introduced. For the record type, 4 different input possibilities exist, which will be described next. So first, I define a load case number under which the results of our pushover analysis are saved. The input type VBU gives me the base year control node displacement diagram. For this, we need to define the pushover load 1001 at the record LCC0, which is the basis load case for the capacity curve. Then I define in LCC1 the first load case of the capacity curve. Then I define the number of the load cases of the capacity curve, which I have parameterized here with the parameter ln. So I can go to the capacity curve report browser and see how many load cases have been created, so 39. So I define here 39, and at the control node I define the node number for which I want to check the displacements, and in our case this node is the number 100, as you can see here, which corresponds to the roof displacement. With the input of the structural performance limits 1, 2 and 3, I define the performance levels of my structure. So we can run the SOFiLOAD. So we can go to the report browser, and for this load case 2001, we get the base year roof displacement diagram. In the pushover-analysis statistics, we can view the list values of this diagram. So we take here the load case number, the displacement, base year, and also the performance level for each load case. In the next input, for the load case 2002, we'll leave all the parameters the same, and we change only the type record to AD, and also we include the response spectrum 101. If we see here the manual, for this input we get the spectral acceleration spectral displacement diagram. We go at the load case 2002 at the report browser, and here we see the demand diagram for Eurocode with 5% damping, and also I get my capacity diagram of the structure into spectral type values. Another difference to the previous diagram is that we can see here also the periods to be plotted at this diagram. In order to find the performance point of our structure, the pushover analysis approach has to be defined. This can be either the Eurocode procedure or the ATC40 procedure. So let's see first the ATC40 procedure. The ATC40 procedure is based in the elastic demand spectrum and an elastic single degree of freedom system with equivalent damping and equivalent period. So what is new here at the push command is this opt, an additional option, and here you can define the structural behavior type of your structure. Then the rest of the commands are the same, except that now at the LCDM we define the 102 load case, which corresponds to the UBC demand spectrum. And we go at the load case 2021, which corresponds to the ATC40. So let's explain a bit what we see here at this diagram. The black line represents the elastic 5% spectra according to the UBC. By performing ATC40 analysis, SOFiSTiK calculates the spectral reduction factors, and using those we take the reduced demand response spectrum, which we see here with the blue line. Also we see 2 points. The one corresponds to the yield point of the structure, and the one in the intersection of the blue line and the capacity demand line represents the performance point of the structure. We also see that the periods are also plotted, and here we can see the Ty and Tp, which corresponds to the yield period and the performance point period. Cf is the effective damping that the program has calculated. Then at the pushover analysis results table we get the most important values from this diagram into tabular results. So if I press this legend option, I get the information for these parameters below the table. So for example, we can see here for Ty and Tp that are the periods associated with yielding and performance point. Also we can see the spectral displacements at yielding and the control node displacements. At the pushover statistics we see again the table that has been already explained, and between those load cases 1136 and 37 stands our performance point. The Eurocode procedure is based in an elastic demand spectrum and an elastic single degree of freedom system. So we define the load case 2011 for the Eurocode procedure, and at the LCDM we define the load case 101, which corresponds to the Eurocode response spectrum. So we go again to the report browser, and at the Eurocode results we get a new graph. With the black line we see the elastic response spectrum, and with the blue line we get the inelastic response spectrum according to Eurocode. We again get the PY and PP points, which correspond to the yielding point and the performance point, and also we get the ductility μ value. Another diagram is plotted, which corresponds to the displacement ductility factor μ, which is simply the result from the division of displacement at the performance point to displacement at the yielding point. Then we get the main values for this diagram at the Pushover-Analysis results. So the performance point is located between the 1135 and 36 load case, and the user can either interpolate those two load cases or he can use one of those in order to take a load case for later design. We can also visualize some of the results regarding pushover analysis in WinGraph. That's why I have inserted the interactive graphic. Under the results, beam elements, implicit hinge reaction, stand several graphical result types in respect to implicit hinges of a system. We can check at this specific graph the implicit hinge reaction moment My for the incremental pushover load. So we can see here that as we increase the load factor of the pushover load, we get higher moment into the implicit hinges. Another interesting result type is the total rotation of the hinges for every load step. Again, we see as we increase the load step, we get more total rotation. Finally, another useful graph is the performance index. For explaining this, we have to go back to the report browser file for the implicit hinges. As already mentioned, a PM interaction diagram has been defined for the hinges at the beams and at the bottom of the base columns. If we check now the moment rotation diagram, we see some indexes into the bilinear diagram. Those are the performance level labels that I already have defined in my workflow in order to control and simplify the evaluation of the hinge reaction. So my first interval is from the 0 to the yield point, and then I give two more points in the bilinear diagram, both for compression and for tension. So we go to WinGraph and we check the performance index graphic, and we double click and check the varying colors. At the left is clear that we get the intervals that has been defined in the workflow. So now, very easily, we can see how the hinges perform for every load step. Also, this differentiation in the color can make the post-processing of the results even easier.